share my screen. Couldn't quite match exactly the links. No worries. That's why we have today, and we're gonna go through some stuff today. Okay, so it seems like more than half of you went through the pre-course material, which is good. I have 26. How many people are in the room? 35. Okay, maybe give it a couple more minutes. But a lot of you didn't go through it at all. All right, well, I think that for those of you who took a break, that's good. But you'll have a little bit more to go through today. The sprint challenge is, not the sprint challenge, excuse me. The homework exercises for today, they're actually not too heavy. So I think you should be able to get through it today. And that way we'll be able to get back to hash tables starting tomorrow. And we'll be right on track. And there's a lot to talk about with hash tables, and they're really important. So so hopefully we won't be feeling too behind. All right, let's get started with theory of computation. Now, for those of you who've gone through the material, and those of you who've looked through, or hopefully you've at least skimmed through it, there's a lot of history here, and then we have this is sort of a kitchen sink module, and this is history. This is sort of how computers work. Underneath, like what is a computer? Like what defines a computer? And I mean, maybe you might be thinking, why do I need to know this to become a developer? The truth is, you're probably not on an interview or anywhere in your job going to need to describe, who is Charles Babbage. I doubt that it's going to come up, but this stuff is pretty important for you to understand, especially more so in certain fields. Like for example, when I worked on embedded military hardware, we were on very specialized tablets, and we had to strip down as much of the hardware as possible till we got to a very, 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 very minimal CPU, a small memory bank, and an encryption chip. Just because we didn't want anything else to be clogging it up. And then we had to take the operating system, which was Linux, and strip out everything that wasn't needed, and just get it down to the bare necessities of what was needed to do the job at hand. So when I went to college, I originally thought I was going to go into robotics, so I applied to most colleges as an electrical engineering major, but it turns out that I really didn't like electrical engineering very much. It was a lot less messing around with lasers and buzzsaws, and a lot more math and signal processing, and I just didn't find it that interesting. But luckily at Berkeley, you're not allowed to just major in electrical engineering. You're forced to major in electrical engineering and computer science. So it turns out that I really liked computer science. There's a lot more instant gratification in that, in a couple of hours, you can write a fully fledged program, whereas there's not much of anything you can do in electrical engineering in a few hours. You need to get a lot of different, do a lot of math, do a lot of signals, send it out for fabrication, and then in the end, you probably have a tiny little thing that makes a light blink on and off when you want it to. So I ended up switching almost completely over to computer science. That said, what I really like about what we learned there is that we were able to understand everything that goes on from the very high level, working with Python and whatnot, and then down to C, and then even lower, we went to assembly, and then from assembly we went to VHDL, which is down to AND gates and OR gates, and then down to chip fabrication, and even further down to transistors, and that really helps kind of connect everything that was going on for me. like what's going on in a computer, right? Like, okay, I understand there's a keyboard and a screen and then some box with some electronics in it, but what's really going on inside of there? And you know, we're squeezing all of that into one day. Obviously, we're barely even scratching the surface. You know, we're just giving it a quick look and we're moving on. But hopefully, you'll get a better sense of sort of what a computer is, where the roots came from, and what can, and maybe more importantly, what can't be done with a computer. Thomas, to answer your question, what distro of Linux do we use? I forget. It was some mini. Had some funny name like Mini Linux or something, or Micro Linux. It was made for embedded devices specifically, and I remember it had some cute, funny name, but I don't remember what it is. But that was it. Didn't even have Vim on it. We just had VI. We couldn't have all of the fancy features that VI improved. So anyway, no, it wasn't some special ultra secure kind, but because of the nature of Linux, where all the guts are exposed, we could take everything out that we didn't need, and we only had things that we did need. And then, you know, you can see the source code, so you can see like really everything that's going on. And then the secure part was a chip. Like there was a secure chip that that at the time I wasn't even allowed to look at. They had it in a secure room with like a crazy lock. I don't know what I would have gotten from like looking at this chip, but there's some pretty strict security measures around it. So anyway, let's start looking from theory of computation. Even though about a third of you haven't gone through the material, I recommend you take a look at it because it's pretty interesting stuff. And there are some nuggets in here that are very practical that I'm going to talk about a little bit more in depth than some of the historical things. So back in the 1800s, back before computers, before transistors, before any of these electronic things, that was sort of during the Industrial Revolution, right? And there were a lot of calculations that needed to be done. And, you know, calculations were done by hand by people. And even if you had very good calculators, human calculators, there's still going to be errors. And errors could be very costly, you know, for money reasons, for safety reasons, for a number of reasons. Which is why some of these scientists and engineers wanted to find a way to do it better. And there's a lot of things we take for granted, right? Like a pocket calculator seems so simple, but when I think about it, I'm not sure if I would know how to build a pocket calculator from scratch. You know, even though I have a 4-year degree in supposedly electrical engineering and computer science. And you know, these folks didn't even have the benefit of that. Like they're starting really from first principles. We talk at Lambda that we start from first principles, but these are like way before even those things. So some of the folks we're talking about are Alonzo Church and Alan Turing, Kleene, Gödel, Hilbert. These are all very important figures. Alan Turing, in specific, you'll hear his name brought up a lot. If you're talking a lot of languages, like you may hear the word Turing complete referred to. Turing complete means that you can basically, any problem that can be solved using a computer, we're going to talk about what solvable problems are, that language can solve it. So, for example, C is Turing complete, Python is Turing complete, Scheme is Turing complete, assembly is Turing complete. There's a few key characteristics that a language needs to have in order to be Turing complete. And that basically goes to the Turing machine. Are there any that aren't? Not that are used in the way that we talk about programming languages, but if you look at some, like if you have, you may have something like without persistent memory, or you may have a language that doesn't allow you to do a loop, a for loop, things like that. I guess like, okay, you can think of a calculator as a programming language that is not Turing complete, like a regular basic pocket calculator. Like you can put in the inputs and you can do 5 times 7 and get 35. which lets you do arithmetic operations, but it doesn't let you store variables and do operations on variables. It doesn't let you iterate and do loops, things like that. Is HTML Turing complete? HTML is not Turing complete. Because HTML doesn't let you do all of those things that we mentioned. So that's, yeah, a lot of people say, like, you know, I know HTML and CSS, like, is that programming? Is that, like, it is coding, in that you're encoding something with, you know, with letters and numbers and symbols, but it's not Turing complete because, you know, you can't do all of these operations with it. JavaScript, however, is Turing complete. And I guess if you use a scripts tag and you're writing JavaScripts within your HTML, I guess you could consider it Turing complete in that way. But just writing JavaScript or CSS is not actually Turing complete. So that's an important distinction to know. I guess that's maybe the difference between a coder and a programmer. Maybe not. I don't know. Okay, so from there, Turing created a definition of something called a Turing machine, which is basically what we talked about. We have persistent memory, which was represented by tape, and this is a literal tape where, like, you would stamp, like, letters and symbols on the tape and then move along the tape. It was a very slow and laborious task, but at that level, it was more conceptual, and then you had some physical mechanical machine that would do operations based on given instruction sets. It would read data on the tape, and then it would return a value, and that was a Turing machine. And that's still how computers work today, right? We have a processor, which is your CPU. You have your tape, which is memory, and then you also have disk, which is a slower form of memory. And then you have your inputs and your outputs. Your inputs being like a keyboard, and outputs being your monitor. Of course, there's a lot more complications there, but at its core, you know, we're still using the same Turing machines that were devised way back when. So I think when you're thinking about like code and all of these crazy problems that can be solved, it really boils down to that. You have some memory on tape, and then you have a processor, and then inputs and outputs that process based on that. And if we go a little bit further down, okay, where do we talk about Babbage? Okay, Charles Babbage. Babbage created an actual physical machine which was used to implement this, which was his the analytic engine. The difference engine came first, which was basically a mechanical version of this idea of a Turing machine. And then Ada Lovelace worked with Babbage to program it. And as you may have known, of course, I'm skimming over this a lot. The difference engine was not totally Turing complete because it wasn't able. It couldn't do loops and it couldn't iterate. But we had the analytical engine, which was meant to improve it, but it was never finished, unfortunately. All right. I think if there's any questions about this, you can look. There's of course tons of Wikipedia material and other stuff out there. If you want to look more into these folks, I think they're really interesting. And this is something I think. If you're thinking like how is this helpful? One thing that that's pretty key in interviews is people want to see that you're interested in computing and that you do have a deep knowledge. And if you're able to talk about these things, I think that's a pretty you're probably not going to be asked a specific question, but if you can go into these things, a lot of programmers are pretty nerdy people, and they like a lot of nerds or geeks. they like to get into the history of these things. So if you're starting to use words like, oh, this is a Turing complete language, or, oh, I just want to think about it like a Turing machine, like these things can really help them show that, all right, you're a serious programmer. You're not just some boot camp grad who learned the superficial basics. Like you're a real computer scientist. That's about all I'm going to say about that. Boolean algebra, which was, I guess it's named after George Boole. Augustus De Morgan has done a lot of cool stuff in math. They have come up with these sort of logical symbols. So you have a question down here. Where have you seen Boolean algebra used in JavaScript? And what are some examples of logical symbols in JavaScript? So I'm going to put that to Slack. Where do you see Boolean algebra used in JavaScript? And what are some examples of logical symbols? JavaScript, Python, they're pretty similar. Yep, double ands, double or, double pipes. Yep, the bang symbol. So and is this up caret. You can remember because it looks like an A, and this V is the or symbol, and this sideways L is the not. If statements, yes. A implies B, so that's like saying if A, then B. And then this double one is if and only if. So yeah, you got it. These are used a lot in conditionals, in while loops, in for statements. One important thing that I'm not sure if we get into here are truth tables. So truth tables are, you can say, like you have A and B, and if you want to do the truth table for A, then you can do something like A and B. It would be, so if A is true, I'm going to do ones. B is, you start with 0, 0. 0, 0, 0, 1, 1, 0, and 1, 1. So if you're doing ands, A and B, this is 0. This is 0. This is 0. And this is 1. All right, so this is a basic truth table. And what this is saying is that for A and B, if A is 0 or false and B is false, then A and B is false. If A is false, B is true, it's false. A is true, B is false, then you have false, and only if A and B are both true does A and B equal true. If you want to do or, it's the same, except this is true and this is true. And more, you can do this, which is the same as XOR. We'll just put XOR. XOR is false for this, true, true, and false. You can also do not A, which is A and not A. If A is 0, not A is 1. If A is 1, not A is 0. So when you think about, I know that a lot of you think about, it's pretty intuitive, right? When you think about A and something, or A and B, or A or B, it sort of makes sense because it's very related to how we speak English, right? Like if you say, if I have time and I have money, then I will go to the movie theaters. Or you could say, if I am hungry, or if there is a slice of pizza on the counter, I will eat the pizza, right? Like those, you don't even really need to think about those things too much. Um, but when you really boil it down to logic, um, always, to answer your question quickly, it's because that's how they're represented in memory. So again, computers can only store ones and zeros. So zeros are representative of false, and ones are representative of true. And Sabat, that's actually a really good question, because that's what we're going to be getting into very shortly. That's sort of where I was going with this. So I'm actually glad you asked that question. So when you get to what does it mean for a computer, right? Because when we talk about these things in English using if, and or, and or, we're using these English semantics, right? But computers have no concept of semantics, right? Like they don't, like I guess Sibat, to answer your question, like it doesn't know about true or false. All it knows about is 1 or 0, right? And what a 1 or 0 actually means, like in memory, it's either all right, this transistor either has charge or it has no charge. And because we're talking about electricity, it's not a physical switch. It's like if the charge is above this certain threshold or if it's below this certain threshold. Usually 0 means like ground and 1 means charged. So I want to, I'm going to take a step into what we're talking about with electrical engineering. So transistors. So how many people know what a transistor is? I'm curious. What's the best way to do this? I'm not gonna make a poll. Define no. Okay, I'm gonna assume that no one really knows what a transistor is here. Okay, so basically a transistor is it's this little electronics component, and you'll notice there are 3 prongs here. And what that means is you have an input prong, you have an output prong, and you have a charge prong. So basically, the charge prong is just powering it. So it's like you're plugging it into the wall. Not actually plugging it into the wall. It's just like it's connected to the battery that's plugged into wherever. So that's basically setting what a 1 is. So this is, you have the input charge, and then you have input and then output. Now, if you have, if it's charged and you have an input, then the output will be charged. And if there's no charge, then the output will not be charged. Okay? You got that? Let me see if there's a better diagram here. Okay, here we go. So we have this input, we have the charge, and then we have the output. This is actually ground. This is grounding. So this is just setting what a 0 is. The charge is what a 1 is, and then based on the charge, it will either be, the output will either be charged or uncharged. And again, that means 1 or 0. Now this transistor is the basic building block for every single computation, every single computer. Now to get at what that means, we can look at an XOR gate. So again, if we look at our truth table, an XOR is basically true if 1 is true and 1 is false, and not true if they're both true or false. Now you can create an XOR entirely using transistors. I'm not going to go through all of this, but each of these components is a transistor, and you have an input 1, input 2, and you have an output, and then the output is based on the truth table. So if 1 is charged and 1 is not charged, then it'll output charged. If they're both charged or if they're both uncharged, then it'll output uncharged. And that gets you an XOR gate. Now that could be cool. Thomas recommends a link. So the cool thing about XOR chips, about XOR gates, is that you can create an AND gate or an OR gate using purely XORs. So that in that way you can create ands and XORs, ands and ors, and also knots. You can also create knots. Um, now, if we have ands and ors and knots, we can create an adder. So what an adder does, let's look at what an adding does. So for adding in binary, so that's base 2. We're used to base 10, but for adding in base 2, we will do it like this. 0 plus 0 equals 0. 0 plus 1 is 1. 1 plus 0 equals 1. And 1 plus 1 equals 1, 0. Right? This is another truth. So if we look at this as a truth table, we can see this is the base value, the added value, and then this is the carry value. So if we see a basic adder, we have 0, 0, 0, 1, 1, 0, 1, 1. We can see that the sum looks like an XOR, and the carry looks like an AND gate. Are you following so far? Oops. For those 10 people, hopefully, for the ones, hopefully we'll be able to follow. So basically, if we look at this, so we see the sums are an XOR, and the carries are an AND gate. So this is a really slow site. So we look at it. It comes into this is what an adder looks like. These fish-looking things are XORs, and these Ds are ANDs, and these fish with no tails are ORs. So basically, the reason that we're looking at this is because you can see when we're talking about the calculator that you can build calculators purely using these logic gates. Basically, ANDs, ORs, XORs, and NOTs. And through that, you can. So we just talked about an adder, but you can actually do every single integer arithmetic sign using just these gates. And it's actually a pretty fun exercise to try to build one of these on your own. Like, I wouldn't recommend actually doing it with chips, but you can buy your own gates and put it together on a breadboard and come out with things like this. And based on this, you can create like a calculator, and that gets back to what Babbage was doing. So Babbage made this purely with mechanical operations. Now these inputs will come from different places, and inputs need to be routed from instructions, and instructions are, then we get up to assembly language, where you have instructions. You have a certain set of you only have a limited set of instructions, and based on those instructions, it'll route it to certain parts of the chips. And these chips all get fabricated, not these chips, these transistors, these transistor formations all get fabricated onto a chip. And if we look at Moore's law, you might have heard of Moore's law. This is a pretty important thing too to realize. So Moore's law states that the number of transistors on an integrated circuit doubles approximately every 2 years. Now let's look at this. This is up to date. Okay, this goes up to 2016, but you can see all the way from 1970, we've kept up this roughly steady upward curve. Now what that means is that computers are getting faster. Computers keep getting faster, and it seems like they're going to keep getting faster for the near future. And what that means for developers is that when you're building things, especially for things like mobile devices or for computers, you understand that they are getting faster. Also, things like storage are getting cheaper. I think there's Moore's law for data storage as well. Let me see. other formulations and similar hard drive disk density. So this is telling you that 15 years ago it cost like $100 to get 256 megabytes flash drive, and now you can get like a terabyte for I don't know how much, $50. So that's an important factor of Moore's law. But I guess when you look back to what we were saying, how many transistors are on a chip now? On the Spark M7, we have about 10 billion transistors. 10 billion transistors is crazy, but all of that formulates a little chip, and it's like this big, and they get fabricated and stamped into these things. And then chips have the little like spider things on the side. Those are a bunch of inputs and outputs. And when you talk about like how many inputs you have, that's how many inputs you can have to your where is it? Where's our adder? To our adder. So we have A and B. You can get multiple inputs and outputs, and like you can have 64-bit inputs, so that'll have 64 inputs and outputs. Yeah, Vim, Moore's law is starting to taper off, but I mean, they're coming up with cheats. So now you have like multi-core processors. So I think that they're, when you just, instead of one chip, you have two chips. And then that's sort of cheating as far as computer processors. And you're also not getting double the performance from that, because there's a lot of that extra performance is spent just managing between those performance things. And you have multi-threading, and now a lot more there's distributed computing, and like you offload stuff to the cloud, so things go to cloud. So in general, computers are still getting faster. But yeah, I mean, at a certain point, there's like physical limitations to, like, we're getting to like the molecular level now. But yeah, and if you look at how a transistor works, it's using a semiconductor. So the semiconductor will conduct if it has charge, and it won't conduct if it doesn't have charge. So that's what a semiconductor is. And the semiconductor most often used is silicon, which is where Silicon Valley comes from. So so that is, that was in about 20 minutes, the entirety of the electrical engineering half of my computer science degree, of my electrical engineering computer science degree. So, so that's that. How much is due to consumer applications not needing greater speed? You know what? I don't think it's that, because even now, like my phone, I have an iPhone 6, and that thing is chugging now. And part of it is probably just like hardware degradation. But Gabriel, I think you posted this, right? Where there's a lot of like junky code that has that's just super inefficient, and a lot of programmers take advantage of the fact that computers are so fast, and they just write really inefficient code. Like they'll have big O n squared functions where it could be optimized to run in big O of n, but they're like, it runs fine, so I'm not going to optimize. Which is I don't know how I feel about that. I think once Moore's law, once we hit that tapering off point, and we can't squeeze much more performance out of hardware, then maybe software will need to improve. But for now, it really doesn't. And then you're going to have people on the other end who are always going to try to squeeze out more, right? Where like you want to crank, you're playing some super high definition like Crysis engine, or you want to play Skyrim with new texture mods, and you want to crank it up as high as possible. So people are always going to be doing things like that. There's also so one thing that we didn't talk about here is the clock speed. So we have these what are we doing? We have these adders. So these operations, it's not a continuous stream, right? Like you have these things have to change, and they change on a clock. So you have up, down, up, down, up, down. And that's when you see a processor is like X gigahertz, that's how many operations it does per second. So gigahertz is 1 billion operations per second. 1 gigahertz, that means 1 billion operations per second. So that means it flip-flop. It's called a flip-flop. It will flip-flop that many times. And that's, so each of these, when you're adding these digits, it can basically only do one at once. So we're going to do, it can't add like this whole thing at the same time. So it needs to do it in sequence, because first you need to get the carry, right? So you solve this and you get the carry, and then with the next one, you have to add that up, right? It's just like you're doing in elementary school, right? You have to add this column up, you carry the one, then you do this one, you carry the next one, you do like the computers have to work in the same way. And that's where the flip-flop comes in. Every flip, it can do one operation, and then it goes down, and then it'll do it again. So when you think about, all right, you have a 4 gigahertz processor, and again, a lot of those hertz are used for internal processes. That's what's going on, right? So when you have a for loop, and you want to run a bunch of code within your within that one within that loop, like say you want to iterate 60 times or something, and you want it to happen instantly, which is, let's say, in 1/60th of a second. How many operations are you doing? Every time you're doing an add, that's one operation, but actually, if you're adding a 32-bit, it's probably like 32 flip-flops. But again, when you have a billion or multiple billions per second, that goes pretty fast, and you can do a lot per second, but it's not infinite. And when you look at Big O, you can see how things like n cubed, like that stuff can easily get up into billions. But that's also why we don't really look at the constant value that much, because add you think of as one operation, but if it's 32 operations, you don't really care about that 32, right? And then something like doing a square root is more expensive than an add. Obviously, there's like hundreds of operations that go on in that. And then also, so I said that these things happen, like these take a lot. Now there's also specialized hardware, which is what graphics cards are. So graphics cards they have special chips with these operations that are used a lot. And then they have, when you do these calculations in hardware, they're way faster than doing it in software. That's because you can route them through these specialized chips. These specialized, like, specifically formulated hardware to do these operations. Okay, so those, and then all gets back to, that all really comes down to what Babbage and Ada Lovelace and Alan Turing and all of these folks were getting at. Of course, as powerful as these things are, computers can't solve everything, and this is something that's important to think about. I mean, maybe more in fields like machine learning and AI, they're trying to answer these unanswerable questions. But you may be at a company, especially if you're doing like an early stage startup or like a new tech kind of thing, where the CEO has a great idea, like a crazy idea, and he looks at you, the programmer, and says, "Hey, can you do this?" And maybe you will say, "Yes, but we need more money, and we need more people, and we need more time." Or you can say, "No, that is not calculable. Like, a computer can't do that," right? At a certain point, some of that is common sense, but if you want to get specific, you can look at where is it? At what Alonzo Church and Turing got at. Church. Where is that? Church Turing thesis and computability. So basically, this is saying that this is a simple proof that could be interesting, where you're saying, like, what is calculable No, it is not. I'm not going to go too deep into it, but I think if you think of a Turing machine, like the definition of something that's calculable is something that can be calculated using a Turing machine. Something that has a finite, a defined scope, and you know, a set of memory and the set of operations. And if you can figure out something within that, then yes, it's calculable, but it may not be. Um, what else? Oh, we haven't even gone through this first part. This is the software things. Okay. Are there any questions about any of this? About, I guess, you know, a lot of the historical things I think you should look up on your own. But does anyone have any questions about maybe some of this hardware stuff that's not in the notes? Hardware, transistors, adders, chips, not that one. Any questions about like how computers work? How like at the base level? I see some people typing. Uh, I'm waiting. I'm very excited to see what people have to say. Sure. Clocks, flip flops. See if we can Google it. Let's see. CPU flip flop. See if flip flops and registers. Let's look at this. Okay, this doesn't seem like it has very good. Okay, I think this is okay. This is sort of what I was looking for. Like you have this flip flop. So again, this thing at the top is a 1, and at the bottom is a 0, and you're basically giving a charge and no charge, charge, no charge. Um, and so one of my projects in one of my early double E classes was to create a flip flop. And the way we did that was you can build it, excuse me, using entirely base electronic components. So like you have a resistor, you have a transistor. Wait, okay, I forgot. There's a reason that I didn't go into double E. But basically, using pure electronic components, you can create a signal that goes up and down, and it has these nice peaks and valleys, and that's what tells your computer to update in the chip. That's how you make your transitions from instruction to instruction. And certain things will take like certain number of instruction cycles to go. Again, that's what your computer is referring to when you see like so and so gigahertz processor, and it's possible to turn it up. With computers, you can overclock it, which means you crank it all the way up. But you know, you're getting into the hardware at this point, and if you overclock it too much, then you risk like melting your hardware components. But that is sort of the limiting factor of every instruction. So at most you can do like one instruction per flip or flop. You have ALU. That's I think arithmetic logic units. It takes the clock as an input, and then that's what it uses to change these states. Again, there's a lot of. I wonder if this link that Thomas posted, maybe they'll go into that a little bit, but yeah, I mean, in general, you probably need to know as a computer programmer is that more faster clock speed allows you to do more stuff, but it's not a one-to-one thing. Like this is why we do big O, is because you can't count like, okay, I have this many gigahertz to work with per cycle per second, and I have this many instructions. Like, you know, you can't do the math to figure out like, all right, how fast will my code run? So it's not terribly important, but it is important in the sense that you can see, all right, that's what's going on underneath. I think if you saw probably Babbage's physical things, you can see like each thing, like they'll move on a much slower clock. Thomas, so might some things that aren't currently calculable ever be calculable? Like if a new way to solve the problem is discovered? That is a really good question, and I think that's maybe the deeper level of that's how this is evolving. If you look at Ada Lovelace, when people were, you know, these questions people were asking about, like, is AI going to take over the world? You know, are the machines going to uprise? Like, these were being asked way back when. And you know, Lovelace said, no, this is not intelligence. This is just a mechanical operation. Like, there's no way to have intelligence in a machine like this. Turing also created something called the Turing test for AI, which is, I mean, the test is basically this. If you're chatting with a bot, if you can't tell that you ask a set of questions, and if it's impossible for you to tell if you're talking to a bot or if you're talking to a human, then this AI has reached true intelligence. Now, not even that long ago, that would have seemed impossible. But now, with machine learning, it's getting more possible. And maybe it's just maybe Lovelace didn't think this was possible because back then their machine could only do like a handful of operations per second, whereas now, you know, thanks to Moore's law, thanks to innovations in cognitive science, brain imaging, things like that, not only do we understand more how the brain works and how language processing works and how people learn and how memory works, but now we have processors that are incredibly fast. You know, we have vision, machine vision that's really that's getting really sophisticated. So I mean, maybe things that can be solved can be solved. Maybe it is just framing it in the right way, and that could help. Like if you say, you know, can we do something that does this? You can say, all right, well, we have this, you know, we have this imaging, we have this language processing. If we have those components, if we can put them together in an interesting way, then I think that it's I think, yeah, we are as a society now solving a lot more interesting problems that probably were unheard of even, you know, 10 or 20 years ago. All right. Well, let's move on. Let's move on to state machines. So state machines are kind of cool because these are also a lot more useful in double E, where sort of the input to outputs are much more complex. Like processing, you have to do a lot more things manually. So a lot of times you really have to plan things out. And then like if you're creating an elevator, for example, like a chip that handles an elevator, you'd probably draw out these. Well, first you would start by drawing out a state machine diagram, and then you would program a truth table based on that. And then you would figure out the chipset that will matches the truth table that you want. And then you would fabricate it. And then, you know, you would hook up all of the wires, and that would be your the controller for your elevator. These can also be useful to think of for programming. And is it here, or is it in your? It might be in your. Okay, yeah. Here's the challenge: to draw a state machine diagram for a video game AI. This is actually how a video game AI works, or how a lot of it is drawn out. Like if you use an engine like Unity, the way that if you're not a coder, they have AI scripts that allow you to do different variations based on states. Same with animations. Animations are all done using state machines. For example, if you're if you're doing a jump animation, you're in the air. If you're going up, then you're playing this animation, and if you're going down, you play this animation. And the state transitions are all done using state machines. Now, the state machine, you have certain states, and then you have transitions, and that's about it. Finite state machines are defined that each state, that basically there's a finite amount of states, and you can think about something that has an infinite amount of states. Like, all right, you have one, you start with the number 1, and then you have this transition that's add 1, and then you have 2, and then add 1, and you have 3, and then you can keep adding 1 forever, and you have infinite. Now, you may think, well, that's how a computer works, right? But actually, a computer is limited in how much you can add. For example, if you have a 32-bit integer, it can only go up to 4 billion and whatever. So even though 4 billion states is a lot, you'll get stuck. And then you can say, well, maybe you can represent it using more than 32 bits. Like, let's say you have a 1 gigabyte hard drive. Let's say you want to use all 1 billion of those bits, of those bytes. So that's actually 8 billion. Well, it turns out that even though 2 to the 8 billionth power is this huge number, it's still finite. So all computers are finite state machines. And states are defined, if we think back to the Turing machine, states are defined by like, all right, what's on the tape and what state. So on the tape, you have persistent memory, which is things like disk, and then you have active memory, which is like the memory on your hard drive, not your hard drive. It's like your actual memory. So you have disk space, and then you have your memory, and that's holding your state. And inputs and outputs just cause transitions between them. You may also remember from object-oriented programming, you make changes to your object, and it changes your object state, right? Like, you have your player object in your adventure game, and then you eat a sandwich, and now your player has strength plus 10 or something. And now if it tries to pick up, maybe you tried to pick up a rock before when you had strength of 0 and you couldn't pick it up. But now that you ate your sandwich, now you're to the state of strength 10, and now you do pick up rock, and then you're able to pick up the rock. So these have a lot of applications all throughout programming. And for certain things, for certain kinds of coding, like AI in particular, it can be really useful to think about things like this. In general, like, when you're writing an essay and you're outlining a paper, you want to draw your mind map, or I don't know if you've done anything like that, but you want to draw your outline, and these can be really useful for drawing out things like that for certain kinds of programs, like for vending machines, for example. I think that there's not a whole lot to say about these things, about state machines. Are there any questions about this, about state machines? For people who haven't gone through it, I'm moving through it pretty quickly. Yeah, I think these are really straightforward. I think they're pretty straightforward. I think that a key to remember is that any code you write. So remember back to Turing's thesis that anything that is computable can be, the definition of something that can be computed is something that can be solved using a Turing machine. And anything that can be done with the Turing machine can be represented with a finite state machine. So any code you write, any single code, no matter how complicated, can be represented with a finite state machine. So if you get stuck, trying to, how do I solve this? Maybe if you're thinking about like some crazy algorithm, or maybe, you know, you're implementing a really a really complicated input output module for a client, and you're just getting overwhelmed. It may help to step back and think about it like a finite state machine. So think about, all right, what are my states, and what are my transitions, and what are my rules? What can go where, and how do we get there? What are the inputs? How are they processed? And what are the outputs? Um, any problem, any computer program at all can be reduced down to these, down to a finite state machine. So if you find yourself overwhelmed, like how can this be done? Just take a step back and think about it. It may help you just take a step back and to just start drawing it out. You know, especially if, you know, the code is starting to blur, and you know, you want to step away from the screen and just get out a pencil and paper. And any computer program can be written out like a state machine. All right, so we'll take a break now, and then when we come back, we'll go through some regular expressions, and with the time we have left. So I think that the best use of our time, when we go through regular expressions will just be to go through some examples. So we'll do that. But first, let's take a 5-minute break. All right, and we are back. All right, so far we have gone through quite a bit. We've gone through some Boolean algebra. We've gone through abstract computing and the Turing machine, what it means for something to be computable. We've gone through truth tables. We've gone through hardware. We've gone through how a computer works all the way down to a semiconductor level. Gone through some history, and then we've gone through state machines. Now we will get to, now we're looking at regular expressions. Now regular expressions, so this curriculum predates me, but it's, you know, it's a little bit funny, like how it's, where it's stuck here, because a lot of this is really, a lot of the stuff we learn is really abstract and kind of soft, where then we get to regular expressions, which are a really extremely practical, like nuts and bolts kind of thing. And I mean, it's neat that, I think, where is it? It's useful because you see, here we go. You see that regular expressions can also be represented and thought of pretty well as a finite state machine. So I suppose that's where it fits in. But we can, I think it's good for us to be thinking about these in this way. This is also a pretty cool example of, like, all right, how are computers looking at these things? Which gets down to, like, all right, how is it making these calculations, and such. So let's start with these basics of regular expressions. First of all, what is a regular expression? Regular expressions, or regex or regex. I'm not sure which is the actual pronunciation. I Googled this. Is it regex or regex? And there seems to be no consensus on the internet. I say regex usually, just because it's like regular expressions. But I know a lot of people who say regex. I don't know which is popular. It's like tuple and tuple, or GIF and GIF. I sometimes switch how I say it as well. Anyway, regex is basically pattern matching. So if you're searching for something through for a specific pattern through like a massive thing of text, regular expressions are a good way to look for them. Regex is, a lot of programmers really like this, because, especially like those who are using Linux and things like that, because regex allows you to do some pretty powerful things. Like if you're searching through your entire file system and you want to find all of the files that match a certain pattern, which, you know, in Linux, a lot, like different flavors of different distributions will have these files located in other places. If you're good with regex, you can do some pretty cool things. The people who tend to like these are also the kind of people who tend to like things like Vim, or like obscure little obscure programs that are super technical and super esoteric, but once you get good at them, they're extremely efficient. And there's a few practical purposes too. For example, if you're doing web, there's pattern matching for email addresses. That's a very common That's a very common use. In fact, I can show you for one of my projects. Let's see if it's here. Okay, maybe don't. Let me look in one of my, not here. App models, user.rb. So this is the user model for one of my personal apps. And here I'm using this valid email regex, which will, which I did not write myself. I just Googled it. What is a valid email regex? And it seems to work. XKCD, always awesome. Oh, fun fact, I have the same birthday as Randall Munro from XKCD. It's coming up in 8 days, so happy birthday to us both. I remember this one. I remember this one. This is a classic. I like the old XKCDs a lot. I'm impressed that he's still going with these. Okay. So let's go through a few examples. I'm gonna give the disclaimer and say that I'm not the best at regular expressions, and there's people who are really good at it, like Beej, who know these things off the top of their head. But this is something that I can never remember. And my process for figuring out a regular expression is probably pretty close to what you're gonna do, which is I see what I need to do. I put it in a regular expression tester, and I keep hacking away and changing things until it ends up working. Which I actually think is I think is a perfectly fine way to do it. But we'll go through a few examples and maybe talk through what the optimal way to think through these things are. But first, let's go through this list. So we let's get an evaluator up so we can take a look at these things. So if you look in the training kit, we have first Wikipedia, which has all of these things. These are not a comprehensive set. There's actually a lot more. It's not here. Yeah, there's a lot more different specific things, and there's language specific like this. Will give you words. But these are the basic set. And this is what you might be concerned with. This is all you will really need for your homework and your sprint challenges. So we'll spend some time on this. If you put something in brackets, it will allow you to match a specific letter, A through E, or A, E, and X will match with this. You can go 0 through 9. And I think these are in ASCII order. I might be wrong, but I think so. You can do something like, let's see, A through Z. So A, S, D, F will match here. But if you put lower, okay, I guess, match any word. Let's take this away. Something that's not mentioned is that you have these tags. So like for global search, you can also put on like case insensitive, which will let it. But see, if we don't have case insensitive on, it will only do this ASDF. But I think if we do lowercase a, value ranges reverse, start code. Okay, I did it wrong. A through Z. There we go. So this is looking in ASCII order. So if you look at ASCII tables, ASCII tables is a pretty useful thing. I've been using this since college. It will show you the ASCII order. So you're starting from this A, which is ASCII code 65, and it goes all the way till lowercase z, which is ASCII code 122. So I believe this will also match like these characters. So brackets, slashes, and underscores. Is that true? Brackets also matches, slashes, backslash, underscore will all match. So that's neat. Numbers are trickier because numbers start here. So I guess if you're okay with all of these symbols, you can start from like 33, which would be like an exclamation mark. We'll match this. Or we can start from like pound and it will not match that. So this is pretty useful. This is nice because it tells you exactly what's going on here. So if you look at the bottom, it will tell you what the match is. So it starts from character code 35 to goes all the way to character code 122. This is basic ASCII, which goes only to 127, which you may notice is 2 to the, let's see, 2 to the 7th power. So this is what's in 7 bits. There's also 256, which has a lot more special characters, and then you have Unicode, which adds even more. But this will allow you to match everything in a range. If you put a question mark, it will match 0 or 1 occurrence of whatever's preceding it. And instead of just a letter, you can also put a group of things in brackets. So if we put let's put a question mark here. This will match, let's make this a little better. Let's do numbers 0 through 9. 1, 2, 3. These are all numbers, so they'll match. This will match. This will match. And if we put a star, it will match 0 or more occurrences. So this is interesting because it matches 1 and 2, but you notice that these are separate matches. These are, this is not, if you put a star here, you'll notice that these are grouped together. So question mark group matches these separately, but a star will match them together. All right, plus matches 1 or more occurrences. I think pretty self-explanatory. Period will match any character. A gotcha here is that if you want to actually match a period, you need to escape it with a slash. You put a star, 0 or more of any character. If you want to actually match a star, you have to put a slash. This caret is the not, so anything in this bracket will be ignored. So this is the opposite of whatever's in here. Caret itself is matching the beginning of a line, and the $ is matching the end of the line. So a lot of times you'll see with any regex, you'll see a caret at the front and a $ at the end, which shows you that it's only matching within a single line. All right, matching patterns within strings. Yeah, so this is a good exercise to start with because it's actually tremendously difficult. We'll start with, like, let's say we want to match an email address. So let's say brady@lambdaschool.com, and we want to match this, right? We can do, first we want to say A to Z, which gives us, and then this plus is, if you remember, 1 or more occurrences of any letter. So plus this is A to Z. And if you'll notice here, so we match this, we're matching this, and we're matching this. But we want to match the entire thing. So we can do at, and then this, and then dots, and this. Again, this dot is not actually a dot. This dot is because it's not escapes. So this will make it a dot. So cool. So we matched our entire email address, right? So what if I did brady2@lambdaschool.com? So this does not work. Neither does if I do capital. Capital B does not match. This does not match. We can do Brady plus tests at lambdaschool.com. A quick note. Does everybody know what a plus sign does when it comes to email addresses? This is a pretty useful trick for when you're testing things on your web apps. Subaccounts, yep. So everything after the plus is ignored when it comes to email processing. So if so my work email is brady@lambdaschool.com, and if I send a mail to brady plus test@lambdaschool.com, that will also be routed to my same email address. So if you want to test multiple accounts for some reason, like you do stuff like ready test 1, ready test 2, ready test 3, ready test 4, and these will all go to your account. So it's just really useful for testing purposes. Also, if you want to like do filters, like say you're signing up for a website and you want all of the emails from there to be filtered to a specific folder, you can put like I don't know, like what's like maybe you want to make an account at Pusher. You can do like Brady plus Pusher at lambdaschool.com, and it'll go to your account, and then you can filter all email addresses with plus Pusher in it to go to a certain folder, or you can do a from. This could also be a way that you can test spam, where you want to say, all right, is this place giving my email address to like a third party? You can put a plus thing after it, which will let you say, okay, they got my email address from that place. So just a fun test. Okay, so we did all of this. This works. But we want to, all right, all of these are valid email addresses. And some, so let's see if so how can we make these better? One thing is we have this G at the end. You can add an I at the end to make it case insensitive. So that's good. That will get us our first win. Or if not, we can do from capital A to Z. Capital A to Z will work. Capital A to Z. We can, how far do we go with this? Parentheses, all right, parentheses are not handled. Let's go back to that project we had before. So we have this whole thing. So I actually tested this and it did not work in here. I'm not sure why. But I think it's maybe specific to Ruby. I don't know. But we're matching any word character with /w. That's a special thing that's not included here, but you can see here. Gives you any word. And then we have all of these extra symbols that are allowed. Plus gives you any number of instances. They have A to Z /D. What does /D do? /D could mean any digit. Plus and all of this stuff, and then after the dot, we need to have just letters. What does /Z do? /Z matches the end of a string. Okay, and then this, I guess that's just the end of our string. Which one don't they like? So word with the plus. So you can only have one plus in there. I think maybe you can have multiple pluses. Escaped character matches a minus, matches a dot. So I wonder which doesn't like. Matches an @ character. Multiple tokens. What is initial /A? Escaped character. What is good question. Matches the beginning of a string. Okay, so maybe it doesn't like that. Let's get rid of that. Let's get rid of the /Z. Okay, so now we have our first email address it likes. Interesting. What about the rest though? Capturing group. What does this group do? Escaped character matches the dot. That looks fine. Character set matches any character in this set. Matches characters in the range A to Z. Matches any digit character. And matches a minus character. So are you allowed to have minus characters in an email address? This is before the dot and after the @. So I guess you can, because it just has to be a valid domain, right? that seems like it could work. A to Z, this seems normal. Quantifier matches star. Okay, I'm actually not sure why none of these work, even though this one does. Group 1 undefined. Okay, well, what happens if we take some of these away? Does not help us. All right, let's look at just this first half. So that works. Word, alphanumeric. Let's make it global. Okay. Okay, I wonder why global worked. Okay, global does work. So that's nice. What does global do? We can look at regex global flag. G is for, oh, I see. So when we were doing, when we did the first one without the global flag, all it was doing is giving you the first match. But if we do global, it will search everything. Multi-line, we probably want multi-line also. All right, well, what happens if we put this /a back and the /z? /a and /z. No, it doesn't like it. All right, well, for these things at the end are flags, which you may run into when you're going into your Python exercises. But anyway, this is sort of how, like, this is not very scientific, but this is sort of my my caveman way of going through regex. Whenever I find myself having to do it, like I'll go through it, I'll give it a try, I'll just see it until it works. Oh yeah, let's give that a shot. Call him. What's the end is $. Okay, cool. Yeah. So that does work. Did they talk about that here? Matches the beginning of a string, but not an internal line. So this matches the end of a line, matches the end of a string, but not the end of a line. Okay. Oh, maybe it doesn't like the new line. So maybe it doesn't. So I guess the $, will match the end of a string, but this one will match a new line. But don't we have a new line here? Are we creating new lines? All right, well, I don't know. I don't know. Do all of these work? Let's see if all of these work with this email regex. Gotta get rid of these dots. So these all seem to work except for this one. Okay, it doesn't like parentheses. And these do not work. These should not work. Are parentheses valid in email addresses? I don't know. I didn't know that. I mean, my regex doesn't seem to like it, so maybe they're not valid. But according to this, they are valid. I guess that's something we can look up. Valid characters in email address. Low address parts, local parts, subdomain. Yeah, so it says it's not, there's no parentheses. Wait, quotes, parentheses are allowed with restrictions. They're allowed inside a quoted string as described in a paragraph below. Okay, that's, this is getting more deeper than I than I expected. So I suppose like if someone tried to sign up on my personal on this web server and they had a parentheses in their email address, then it wouldn't let them sign up, which would be I wonder if anyone's ever tried that. Okay. Okay, and greedy versus non-greedy. So this is pretty interesting. This is if you think about how finite state machines work. Greedy, let's put this in here. And let's put this contents tag in here. Greedy will start here, and it'll go till the end. Which one are we at? And then lazy will stop. What is this example? I think we only want to look at this. Okay, so this is oh man. You know what? If anyone has these kind of email addresses, maybe I don't want them signing up for my website. Okay, so if we look at this is a pretty good one. So we have these tags here. You notice we wanted to start with this less than and end with this greater than sign. So we want these two Pac-Mans at the end, and then in the middle we want anything in the middle. Now, if we're doing greedy, we have our opening bracket. What are they called? Just greater than. Do they have another word in web coding, or do we just call them like less thans? It seems weird to like maybe pointy brackets. Okay, so we have our pointy brackets at the end of each, and then we're saying we want to allow anything in the middle of these. Angle brackets. There we go. I think that's what I was looking for. So we have our angle brackets, and we want to fill anything in the middle. So this works, but if we want to just look for a single tag, we would want to make it lazy. So so to make it lazy, we put a question mark in here. Now, this is interesting because of how the computer actually processes it, and this is useful if you're thinking about performance. When it's looking to fill anything in here, the computer will go all the way till the end, and then it'll start counting backwards once it reaches these things. But that's why it's called greedy, because it just takes as much as it can. But when you're doing lazy, it will just go until it reaches the first end mark, and it'll stop there. But again, it's useful to remember these special cases, and I think that's all you need to know for at least the assignments. Again, there's more to regular expressions, and if you want to know some of these details, there's some good resources. Like Wikipedia is good. If you Google around, where is it? If you Google around, you can find a lot of good resources. Close some of this stuff. Now, so for your assignment, I'll close this. For your assignment, you're going to be doing regular expressions in Python. So before we go through some examples, let's look at how regular expressions are expressed in Python. So there's a pretty good website on regex1 that will help you do. This is a good tutorial for implementing regex for your homework. So Python 3, import RE, which will before we get to that, are there any questions about regular expressions? I suppose people have been putting them in as we go along. Okay. Anyway, so let's move on to Python. So Python regular expressions, there's a few. It's a little bit tricky to get into. It's not so easy as just dropping it into these regex evaluators. There's some special syntax, and it gets to we have these things like these flags. We have what else? We need to make sure that we're using these slashes. And if you remember, Python treats slashes, backslashes in a pretty specific way. So we need to make sure that we're handling all of those things correctly. So import RE. First, let's look at all the methods that are available to us using our handy dandy dir method. So we have all of these different things. You're probably going to be using maybe match, but probably more likely full match for your assignments. One gotcha is that you want to be using raw strings. So when you put an R in front of a string, it means that it's treating it as raw, and that means it ignores all escape characters basically. So if we're doing like if we do this slash what else, slash a or slash n, let's say, prints s equals slash n. Prints s will print a new line, but if we make it a raw string, it will print actually the string. So we'll make sure whenever you're doing regex that you put this R in front to make it a raw string. What else? We have these flags. Like if you want to make case insensitive, you have re.I is like the case insensitive flag. That's the same as putting this slash I at the end of your regex. I think if you do reg, M is for multi-line. What else? Anyway, I think you can look through these documentations in general. But let's go through an example. So here's a good one where we're looking for dates. So let's define our regex. Notice we're using this R for raw, and then we want to find dates that match this format. So some word, a space, and then some numbers. So we have A through Z plus. So we can have any number of letters, any number of lowercase or capital letters, and we want to have slash D is numbers. You can also do 0 through 9, and then some number of that. So then you call match equals re.search, and then we can look at our match, and we get this match here. Match.group, match.group1, match.group2. So this will show, basically you can just do match.group, and then you'll see what your match is. If we call, so this was our regex, and that works. But we could, I think, we can do like 0 through 9, should also work. I think we can do A through Z, capital A through lowercase z, should also work. Will give us the same thing. Now, one thing you want to, so that's the basics of Python regex. You want to, since you're going to be, for your assignments, let's see, your assignment is here. You're going to be going through all of this text, which is this big thing of text, and there could be multiple. Oh, there's definitely going to be multiple matching strings. You're going to want to use this match all function. Sibat, is it just doing a loop under the hood? Are you talking about this match? It's not doing a loop. It's going through these characters one at a time. So it's saying, all right, what is the first? I mean, I guess it is a loop where it's looping through each character. So it starts from the beginning like J. Okay, that matches, and then it'll go down. It'll go down this, and then okay, it's correct. It's correct. It's correct. It's correct. It's correct. It's correct. And then if it gets to the end, then it'll return it as a match. If not, like if we just did June 24th, then it will return none. So here it's saying June looks good, but now we're expecting some numbers, so it doesn't show up. So yeah, I guess it is a loop. Like if you were to talk about the big O, it would be big O of n times m, n times m, where n is the length of your input string and then m is the length of your regex. But since the length of your input string is probably going to be way longer, you could just say a big O of n. If you have a, I guess you can have big O n of m if like your input string is like something like 1, 2, 3, 4, 5, 6, 7, 8, 9. If you just have a ton of numbers, and let's say your regex equals raw and 0 through 9. Let's say you want to do times 3. So you want to do 3 of these. And then you do match equals re.search all. Is that right? Find all. Then we match. Then you can see, all right, since each of these matches, we'll have, it will look at this first, and then once it's passed there, it'll look at this first, and it'll look at this first. Note that 2, 3, 4 also matches our regular expression, but since it's already done, it already gets to 3, it doesn't go back in search. It's pretty fast. It is pretty fast, and that's I think that's due to how if you look at this exercise where it's doing this, it is, big O of n is generally pretty fast. I mean, how long is our n? Our n is only like 1, 2. We can find the length of this. Len of this, it's only 42. So for to do anything 42 times is pretty fast. Even if each step takes like a number of operations, like it's not too much. Remember my MacBook Pro is doing billions of operations per second, so this is probably not even noticeable. Maybe we do string times equals 1000. Whoops. Oh, okay. String equals s equals. Let's see if we can make this longer and see if we can get it to a noticeable time. S times equals 1000. Len of s. Now s is that. So let's try our regex of this. Okay, that was pretty fast also. Let's see if we can make it even longer. Okay, too long. Okay, my Python is not liking this. All right, I'm gonna terminate this. I think I overflowed probably my computer's memory. Python 3, import RE. Pair regex versus for loops for string checks, and regex was always way fewer operations. It probably is. I wonder why that is. I guess for that you would have to look at what's going on under the hood. And Python as compared to something like C, is doing a lot of cool things under the hood. So strings in Python have a lot of extra stuff going on, which allows you to do stuff like appending them, and all the little tricks that Python has for optimization. But when you're doing regex, I think it's getting down to sort of the nuts and bolts of it. So it's probably doing more C kind of things. And this module, the regex part, used to be in C. So it was actually, you had to implement them in C, but we ended up just doing it in Python because in C, it's a lot harder just to do the basic things. And we weren't trying to get you to do these things in C. We were trying to have you practice regex. So so that's why we moved it to Python. Where were we? Okay, anyway, yeah, I think you'll probably want to use find all for these things. Flags, if you want to do something like case insensitive. Let's see, you can do, all right, so let's copy this. Regex equals this. re.search equals this. I'm going to make this so we only have lowercase here. And now if you do regex.search, you see we're missing this capital J. We could do case insensitive here by doing re.I, which gives us the J. So that's the same as putting the case insensitive at the end. That's what these flags are at the end of our this. This is global, case insensitive, and multi-line. I think that's all you should need to know for your homework assignment. And as far as Python is concerned, everything else is pretty basic Python. So also on this site, regex1, they have some exercises. So I thought with the rest of class time, we have about 15 minutes left. We can go through some exercises, unless, or I could open it up if anyone has any questions about anything we've gone over so far. Again, we squished 2 days of instruction into one, so we skipped over a lot of stuff. So if anyone has any questions about anything we've gone over so far, regex, state machines, history, hardware, computation, anything related to that, anything related maybe to your homework assignments. Yeah, there's anything related to anything. If not, then I'll just go through some of these exercises. Are pattern searching algorithms useless compared to regex, such as the KMP algorithm? What is the KMP algorithm? Oh, Knuth. I wouldn't say it's useless. I'm sure there's some places where this is superior to regex. Some is not. I think one good thing about learning regex is that it's used everywhere. So it's implemented in pretty much every language, I think, and it's also, I think, most useful for when you're doing things in shell. So like, yeah, if you want to search through if you want to grep through your entire file directories and search for, I guess like this, if you want to be a superhero, regex is really good. It's really portable. I don't know if KMP is used everywhere, but I'm sure there's some places where it's used. I wonder if this is used underneath the hood to implement regex. That's something that you can do some further research on. All right. So with the remaining time, let's just go over some exercises, some simple exercises. So we want to, I'm going to put this cheat sheet on the side so we can have our basic things showing. All right, let's say, all right, we want to match all of these. Hi, Jasmine. All right, so we have A, B, C. We can match A, B, C, but we want to match all of these things. All right, so what do we do after that? We could just do something like this, A through Z, star, or we can do A through Z star, A, B, C. But A through Z star seems to work fine. Basics. If we want to match digits, we can do A, B, A through Z, star, and then 0 through 9. Match spaces, equals, and quotes. So that's a brute force. Or we could just do a dot star, which matches any character. Pretty easy. Match a couple of strings that are not all the same length, but we do not want to match this one at the bottom. Okay, so this gets a little trickier. So now we have to start thinking like a programmer. What do we want to match these first three, but not this last one, right? So the first thing we need to look at is before we write any regex, we need to see, all right, what do these first three have in common that this last one doesn't? Because if we just do this, then we'll match every character. We can't do A, B, C. What is, oh, A through Z. We can't do this because we'll end up with the same thing. So we notice that the one thing that these all have in common is that that they have a dot at the end. I guess we would do dot. So we want to make sure that our thing has a dot at the end. So if we put a period, that doesn't work because we need to escape it. So that lets us go forward. All right, next we want to max can, man, fan, dan, ran, pan. So we match AN, and then we want to do CMF. So we can do CMF, which will match all of this. Or we can do knots, DRP. These all work. Again, you notice there's multiple ways to do all of these things. Okay, excluding characters. Oh, I guess this is like what we did last time. So OG, we can do H and D, or we can do not B. Matching character ranges. So we want to do Anna, Bob, CPC, but not A, B, and C. So what do we want? We want something that starts with a capital letter. So A through Z. We want to have exactly one. No, it'll let us match, but we want to match this entire thing. So how do we do exactly one? Question mark, we'll do 0 or 1. B will be 0 or more, and C is 1 or more. But if we want to do a specific number, we can do 1, and then we can do dot star at the end. Matching repeated characters. So here we can do what's up, and we want to do 2 or more, right? So I think there's a way to, or we can do Z plus, so this works. Because now we have 1 Z, and then we have Z, we need 1 or more. Can anyone think of, is there another way to do this? Is there a way to do 2 or more? I think there's a way to do quantities. Denotes the minimum and the maximum. So N can be omitted and M can be 0. So I think we could do, yeah. So 2, yeah, awesome. Next, anyone have a solution for this one? We want to match repeated characters. How do we do that? So we want to make sure, and there's a few ways we can do this. Have I been looking? I haven't even been reading up here. I guess we could just do something like 2 like this. That's probably what I would do. Maybe they want to have an A at the beginning. And then we can just do dot star. What is the same as doing plus? All right, matching optional characters. So what's important here? And when I look at this, I can see, all right, first has a digit, so maybe we want to look to see if something is at the top, has a digit at the front, or we can match something that has a question mark at the end. What are they trying to do? We can do star dot star. Dot star just works. Oh no, we want to skip this, and then we want to end with a question mark, right? Yeah, yep. That's what I'm looking for. That was what I was looking at, Mark. We could also do start with like 0 through 9. Dot star also works. So what's the pattern that we're seeing here? We want to see, all right, what are we looking for? We want to think about it first, express it in words, and then from the words, it's usually pretty easy to match it with the regex. So matching white space, dot star space dot star. Does that work? Why doesn't that work? Space star. Okay, space plus. Why doesn't this work? Like this? Okay, maybe plus doesn't work with white space when we group it. I don't see why. Is this a tab? Is that, oh, because this is a tab. All right, I see. So we can, how do we match white space? Is it, I guess we can do something like this, yeah. So we can do like /t, space, plus, how about that? So that gives us, allows us to do space, plus, and what is this? A bunch of spaces. All right, match, what do we want to do here? Match the string using new special characters. So when we just do successful, okay, what does the first one have that the last one doesn't? One way to, because we can do something trivial, right? Like mission dot star, but I don't think that's what we want. Okay, but then that's giving us this, nothing before mission. Oh, so this is why we do this hat. Oh yeah, that's a useful reason. So we're starting with this. Cool. Okay, next, match groups. We want to capture this, capture this, capture this. So this is dot star PDF and $sign at the end, right? Why is this giving us? Okay, we only want to capture the front though, before .pdf. So we want to use parentheses. Okay, so this is getting away from what we're doing. So this is dot star in the parentheses, right? And then how do we exclude stuff from outside of that? Okay, like this. All right, well, cool. So now we're, how far along are we? So we're almost done. This goes to 12, but we're out of time. I think this is good stuff if you want to go beyond, if you want to go beyond the homework assignment. I think this is going further than what you're expected to know for at least the sprint challenge. But yeah, we went over a huge amount today. We went over hundreds of years of technology, of computing technology and history. We went over finite state machines very briefly. We went over hardware, and we went over regular expressions. And I think if you take a step back, or maybe a few steps back, you'll see that these all connect in a pretty cool way. So I think you should be well positioned to get through the homework assignment. If you didn't get started, I think that you still have enough to be able to get through the project for today. And then tomorrow we'll go over the solutions pretty quickly, and then we'll be jumping into hash tables. So thank you all, and I'll see you tomorrow.